Welcome back. This is 3.3, all about linear programming. We will be able to find the maximum and minimum values of a function over a region, and we'll be able to solve real-world optimization problems using linear programming. Okay, this is a pretty involved section, so just take it in. If you leave this video pretty confused, that's okay. We will get lots of practice in class. Okay, linear programming is a method for finding maximum or minimum values of a function over a given system of inequalities. Okay, so what's going to happen is we're going to graph usually at least 2 or 3 inequalities in a coordinate plane, and it's going to create a section of that overlaps. Okay, sometimes that will be a bounded section like this triangle on the left, and sometimes it'll be unbounded. See how there's an inequality up top and left and right, but then down here it just keeps going on forever and ever. So what happens is this shaded region is what we call a feasible region. So the word feasible in the English language, feasible means something that's possible. So this is all of our possible solutions to a system of inequalities. And then what we're going to do is we're going to have another function that's usually going to look something like this: f of x comma y equals 2x plus 4y. That's just an example. There could be a number of coefficients with x and y. And what we're going to do is plug in our vertices, excuse me. We're going to plug in our vertices to this function that we're trying to maximize or minimize, and then make a selection based off of that. Okay, so here's an example that involves a bounded region. So here we're given a system of inequalities, and it asks us to name the coordinates of the vertices of the feasible region, and then it asks us to find the maximum or minimum values of the function for this region. Because this is so involved, we're going to use Desmos. Okay, we're going to use Desmos to get a picture of what's going on here. So plug in just the inequalities to Desmos. You notice how you have 1, 2, and 3 inequalities, but then down here, that is the function that's going to be maximized or minimized. So we're not going to plug that one in to Desmos because Desmos only graphs in 2 dimensions, and this is actually a 3-dimensional figure. So let's take a look at Desmos, see what this looks like. This is, let's see, I think it's this one. Yeah, so this is our region of inequalities. So we can see right here that we have an overlapping region right in the middle, and then we have 1, 2, 3, 4 vertices. And how to tell something's a vertex is to look and see, is it kind of like a corner? Is it a corner of your feasible region? And so here we have 4 of them, and so we're going to plug these 4 into our function to see which one or which ones are our maximums and minimums. So to help you out with this, I've created this little table for you. It's going to help you evaluate your function at each vertex. So you're going to take your vertices. So we have a vertex at -2, 6, 0, 6, -3, 3, and 1.53. And before I move on, actually, we're going to just quickly sketch a graph of this, even though it's not going to be perfect, because you will be asked to do that throughout many of these practices. So a quick sketch just to give us a feel for what's going on. So here's our y inequality. That's number 1, and then down here we have, it's going to be a line, so our y-intercept would be up at 12, move, let's see, 1, 2, 3, down 3, right 1, down 3, right 1, down 3, right 1, and we end up with a line that looks something like that. And then down here we see our third inequality has a y-intercept up at 6. We move down 2, right 1, down 2, right 1, and just keep going. And these lines are not straight. I apologize for that, but you get the picture, okay? And then what overlaps is in the middle. All right, so just a quick sketch. Highly recommend using a ruler for these. It's going to make your life a lot easier. And then, so back to these vertices. These are our 4 vertices, so we're going to plug them in. 4 times -2 minus 2 times 6. And when we plug that into a calculator, 4 times -2 minus 2 times 6, we're going to get -20. All right, 4 times 0 minus 2 times 6. When we plug that into a calculator, we're going to get negative 12. Next vertex, 4 times negative 3 minus 2 times 3. When we plug that into a calculator, we're going to get negative 18. And then finally, 4 times 1.5 minus 2 times 3. When we plug that into a calculator, we're going to get 0. And now, our final step is to look at these numbers right here. And depending on what the question's asking, we're going to find either the maximum or the minimum number. So this question is actually asking us for both. So what we see here is that negative 20 is our minimum, because that's the smallest number of these four. And then 0 is going to be our maximum. So the way that we would write this solution is like this. Minimum of, and then you'd write whatever this number is, minimum of negative 20 at, and then you'd write the location at this vertex of negative 2, 6. And you have a maximum of 0 at 1.53. So now let's look at an example of a region that is unbounded. The process is pretty similar, except we're just going to have fewer vertices. Okay, so let's plug in this inequality, see what it looks like. Here we go. We see that we have 1, 2 vertices, and that's it. This is not a vertex because it's not at a corner. It's not at a place where all three inequalities intersect. Okay, and so our shaded region is actually going to be this whole middle piece, and it's going to go on forever and ever up here, if you could imagine that. All right, just for the sake of time, I'm not going to sketch this graph in the plane, but you should. So pause the video, copy down these inequality graphs, and make sure that you're clear on how to do that. Okay, I'm just going to look at these vertices at negative 4, 0, 0, negative 6. We're going to plug those in. 9 times negative 4 minus 6 times 0. 9 times 0 minus 6 times negative 6. And that gives us negative 36 here and 36. And I get these numbers by plugging in these expressions. Okay, and again, it's asking us for a maximum and a minimum. So this is going to be our minimum, and this is going to be our maximum. Right, so the way we write our final solution, something like this. Minimum of negative 36 at the location negative 4, 0. Maximum of 36 at 0, negative 6. Alright, pause the video, give this one a try. Alright, hopefully you have taken a look at these inequalities when they're graphed in Desmos. This is what you should have. Okay, so here's a picture of the graph. You have 3 vertices, negative 2, 4, 5, 4, and 5, negative 3. When you plug those into your expression, you get negative 14, 7, and 21. Negative 14 is going to be your minimum, and 21 is going to be your maximum. All right. So I'm gonna cut off the video here and then make a separate one for the word problem. One thing I want to highlight back with this first example, I said that this represents a 3-dimensional function, f of xy equals 4x minus 2y. So I want to plug that in. This is a 3-dimensional calculator. I might have shown you this in class before, but if you've never seen it, it's pretty cool. GeoGebra has a way to visualize a 3-dimensional coordinate plane. And so if you look at it like this, if you look at the plane like this, then we just have our standard xy plane. You can see that we have our x-axis along here and our y-axis along here. But then as soon as we add a third dimension, now we have our x-axis that's kind of running diagonally here. We have our y-axis that's running diagonally along the front to the back, and then we have our z-axis, which is running up and down. And so this light blue plane that you're seeing, it's kind of cutting right through the middle of this. That is our f of xy function. Okay, it's this one, 4x minus 2y. And then all these other blue things that you're seeing, those are our inequalities. Okay, and so you can see kind of that same shape that we saw on the Desmos graph. See how there's like a sort of a trapezoid shaped region that is shaded. we're kind of seeing that here. And so what this is doing is it's testing to see this plane, where is its highest point for its maximum, and it's right here. And then where's its lowest point for its minimum. If we zoom out a little bit, we can see that the lowest point on this plane is down here, that point A. So those are our maximum minimum values. It's kind of a conceptual way to think about this problem. So there's that. We will take a look at a word problem in the next video.